Okay, good morning, everybody. Please take a seat. Take a seat and be quiet so we can get started. Okay. Actually, before we start, today's lecture, I would just wanted to show you some videos that I found on YouTube. The idea came from, I had one of your colleagues who came to my office hours on Friday, and we were talking about modes, eigenvalues, and all those things. And I was trying to come up with some way of explaining in some intuitive way what these modes are, what these eigenvalues mean physically. And the idea came up of talking about guitar strings, okay, or some musical instrument. So let's say that you have a guitar, right, and then you pluck one of the strings, right? What happens? You hear a sound, right? How is that sound related to the eigenvalues of the motion that describe the motion of the string? An idea? What is the sound that you hear? Typically, when you hit a note, what is it that you hear? You hear a wave, right? What is the frequency of that wave? Right, so a note is some vibration at some frequency, right? Okay, that frequency is exactly the imaginary part of the eigenvalue that describes the main mode of a string, okay? Once you pluck the string, you hear the sound, right? So you hear the note. Does that note stay on forever? No, right? It decays over time. The frequency remains the same, right? So the note remains the same. However, the volume, right, the loudness of that particular sound decays over time, right? How quickly does it decay? What does it tell you about the eigenvalue? The speed at which decays is given by the real part of the eigenvalue of that particular mode, okay? So when you play guitar or you hear any musical instrument, the notes that you're hearing are actually the eigenvalues, okay, of the mechanical parts of that particular instrument, okay? What are the note shapes? Let's see if this works. Of course it doesn't. Let me try this. Let's see if the internet collaborates today. Okay, so here you have a string, right? It's attached on one end. Want to lower the volume? Okay. You attach one end to this sine wave generator, and look what happens. You see the shape? Okay, so okay, now they're increasing the frequency of the excitation, right? And then you see that the string takes all these different shapes. Okay? What are these different shapes? These are actually exactly the shapes of the modes associated to eigenvalues of higher and higher frequency. Okay? So when you see the, okay, so let's look at another one. No, let's look at this one first. Oh my. No, we need the internet now, so I cannot. Okay, this is in French. Probably you can read it better than I can. Okay. So this is the first mode, right? You see that all this mess when when this person like it changes the length of the string. What do you think all that mess is? Is the transient where you have a whole bunch of modes that are actually being superimposed one over the other, right? Up to the point where only the one that corresponds to that particular expectation remains the only one. Okay, all the others have decayed. Okay, so this person is having fun with clearly we are changing the dynamic system here, right? Because then you are clamping the string at different places. So for me, the point is that there is this mode shape, right, that determines how the string moves, right, and then how quickly it moves, and what is the frequency of the vibration. That's something that is determined by the eigenvalue. The frequency is the imaginary part, and how it decays over time is actually the this is actually interesting. How it decays over time is the real part of the eigenvalue. Okay. Now, what they're doing here is not only they're exciting this string at a certain frequency, now they will also illuminate it at a certain frequency. So look at what happens. Blah blah. Move a little bit forward. Now they turn on the light, the stroboscopic light. The stroboscopic light means that we have flashes of light at a certain temperature, at a certain frequency. You see that as you tune the frequency of these flashes of light, you tune it properly, what you will see is that this string seems to be stationary. Okay? Because you illuminate the string once every period, right? So then you just see the mode. So they're still tuning it. There you go. Okay? So clearly it's not that now the string is stationary, right? So the string is still vibrating, right? But illuminate it at exactly one time per period, and then it looks like it's stationary, just moving very slowly. Okay? Do you get a sense? So here in musical instrument playing, the notes that you hear are actually the imaginary parts of the eigenvalues of the string or whatever resonant cavity of the instrument, right? How quickly the note decays, that's the real part. And when you look at the string vibrating and what is the geometric shape, that's actually the mode shape, okay? Anyway, just I thought that this was kind of like a cool way of thinking about mode shapes and eigenvalues and all those things. Okay, let's get to today's material. Okay, so what we'll do today is we will look at, so far, in the last lecture, we really looked at what is called the homogeneous response. What is the response to initial conditions? Okay, so now you have no inputs, or you set the input to 0, and you look at what happens if you start your system from some point that is away from the equilibrium condition and let go. Okay, and so what you're seeing is that you can decompose this motion into the sum of a number of modes. Each one of these modes has a certain geometric shape and has a certain temporal profile, which typically is the amplitude of the mode will be an exponential, right? If your system is stable, this will be a decaying exponential, right? If your eigenvalue has an imaginary part, i.e. if you have complex conjugate eigenvalues, then on top of this decaying amplitude, you will have an oscillation with a certain frequency, okay? The frequency remains constant, the amplitude of the oscillation decreases. Now what we would like to do is look at what happens when you also have an input, right? So now you have a forcing input. So you have a control input that makes your system move, okay? What we will see is that, we already know the answer in principle, right? So because we wrote a bunch of integrals over the past several weeks. But looking at that integral, can be a little bit confusing. Doesn't really give you a lot of intuition into what is happening. But what we will see is that if you take a special class of, sorry, I had to activate the pen. Something's happening. Okay, thank you. Sorry, guys, I don't know what happened. Okay, so what we will see is that if you choose exponential inputs, we'll see what exponential inputs mean, or kind of not too far from what you can imagine. What you will see is that if you apply exponential inputs, the response will also be exponential. Okay, so that makes it kind of convenient, and will allow us to define something that is called transfer functions. Okay, transfer function is an alternative way to model linear time invariant systems. In addition to the state space model with the A, B, C, D matrices, that actually makes a lot of things much, much easier. Okay, we look also how you can go back and forth from state space to transfer functions and back. And then we have a little bit of an appendix for the more mathematically inclined that establish the connection with things called like Laplace transforms. Have you ever covered Laplace transforms in other classes? Good, okay. So, okay, the idea is the following. Why we're doing this? So we have real systems, right? A car that we want to control, an airplane, your heating system, whatever. We write down some equations. Typically, these are equations that are non-linear equations or somewhat complicated. You can linearize these equations and get a model, right? So this is the state space model that we have been looking at in this class so far, which is defined really by these matrices A, B, C, and D, okay? So this is a model that you can use for control design, okay? Now, if you just want to use this model and do the control design, this is actually something that is actually, in a sense, this is the preferred method of doing these things today, as long as you have MATLAB with you, okay? On the other hand, if you don't have MATLAB with you, okay, or you cannot do the calculations at the speed that the computer can do the calculations, or maybe you imagine yourself 50 years ago where you didn't have MATLAB. So then how did you do a control design? You didn't really use this, this kind of model. What you use is this transfer function model that is actually a way to make control design very easy to do by hand, okay? Since in this class we will concentrate on things that you will do by hand. In fact, at the exam you will not have MATLAB with you, right? But the point is that the kind of techniques that we will look at in this class are meant to be such that you can just do control design with a piece of paper and a pencil, okay? No need for MATLAB, no need for calculators, okay? And so we'll see how we can make this thing easier, okay? So, if you remember, this at the end of the day is the formula that we arrived at that relates what happens when you have a system. You apply a certain input u of t, right? A certain function u, okay? And this is a formula that gives you what you will see at the output, y, okay? Given maybe some initial condition, x0, okay? In principle, there is nothing else that you need to know. This is the formula. That's it. Do the calculations, put it in MATLAB, you have the solution. You have what the output looks like given input. Now, this looks pretty horrible, right? So this part, this is this exponential. We have an idea of what that means, right? So we covered that in the past, last 1 and 2 weeks, okay? This stuff under the integral, this is actually called a convolution integral, okay? And this stuff is something that, unless you have some special superpowers, probably you have no idea what that means, okay? I have no idea what that means. Okay, so what we will want to do is, now we want to understand better what this part means. So this is the forced response, okay? And the way we do it is, remember, in linear systems, the key characteristic of linear systems is the superposition principle. Is the fact that you can divide and conquer. So instead of looking at what is the response to any arbitrary input, what you will try to do is decompose this input into easy, like a smaller elementary components, such that it is easy for you to understand what is the response to each one of those components, okay? In particular, we will choose these elementary inputs in a way that the output has exactly the same form as the input, okay? And it turns out that these elementary inputs are actually so rich that you can describe any arbitrary input as a linear combination of these easy elementary inputs, okay? So then, once you have done that, use again the superposition principle, and you can reconstruct what is the solution to your complicated arbitrary input. What are these easy inputs? These are what we call the exponential inputs. In particular, we would choose the inputs of the form u of t is equal to e to the power st. Now, a little bit of a leap of faith here is the following, that what I say is that this s, which is the coefficient that you put to the time, right, in this exponential, this can actually be a complex number. Okay, what does it mean? Well, so s in general would be complex. If it happens to have a zero imaginary part, that is, if s is real, right, which is just a special case, then clearly e to the power st is just an exponential. Will be a divergent exponential if s is positive, will be a decaying exponential if s is negative, okay? If s is purely imaginary, right, so s is equal j omega, for some omega, then clearly I cannot apply an imaginary input, right? Maybe I can do that in my dream, right? It's the imaginary input, but I cannot do that physically, right? If I really wanted to apply one of these imaginary inputs, what is it that I need to do? Well, what I have to do is, I want to apply e to the power j omega t, I will just have to accompany it with e to the power minus j omega t, okay? With a complex conjugate, okay? Because I know that the sum of these two exponential with complex conjugate exponents will actually be a real number. In particular, the sum of these two will be given by 2 times the cosine of omega t, okay? This is going back to using this Euler formula, okay? Okay, so when s is an imaginary number, when I write e to the power st, I'm really thinking of e to the power st as 1/2 of a sinusoid, okay? 1/2 meaning that I need to add the complex conjugate, okay? Okay. If s is equal, is a more general complex number, s is equal to sigma plus j omega, okay? Then again, I had to do the same thing. I cannot apply u by itself. I had to think of this as something that I always accompany with its complex conjugate, so u star. Now, if I write it this way, so then this would be e to the power sigma t plus j omega t. I can just decompose it into the product of these two exponentials, right? This would be the complex conjugate. I can pull out e to the power sigma t. What remains in parentheses is the sum of these two exponentials with imaginary exponent, okay? And again, this stuff in parentheses is 2 times cosine of omega t, okay? So when I choose s to be a general complex number, then I can think of this input as 1/2 of a sinusoid with an exponentially varying magnitude, okay, amplitude. Okay? Yeah.
2 questions. First, what is S exactly?
Oh, as I choose, right? So I can choose one input to be, I can choose as an input, for example, a sinusoid of frequency 1 radian per second. Okay? If I choose u to be a sinusoid of 1 radian per second, what would be S in that case? Question for everybody. Huh? How can you write a sinusoid with a frequency? What is? A sinusoid of frequency 1 radian per second. What would be S? What is the S that corresponds to a sinusoid of frequency 1 radian per second? What is the real part of S in this case? What is the imaginary part of S? Oh. Okay, your answer is half correct. Now flip a coin. Which one is one? So remember, so what does the real part of this S tell you? Look at this. It's the growth of the decay, right? So if I say that the input is a sinusoid with a certain frequency, a sinusoid has constant amplitude, right? So what would that sigma be in that case? Would have to be 0, right? Okay? So in that case would be, let's actually write it, right? So if I choose sigma to be, say, J1, okay, J, okay, so then this corresponds to a sinusoid, right, of frequency, so the period will be, this would be 2 pi, okay? It's 1 radian per second. Okay? So this would be time, and this would be U, okay? You get the point?
Yes. What is half the sinusoid of the signal?
Yeah, because I cannot choose, I cannot say that E is equal to, so that U is equal to E to the power JT, right? Because that would be a complex number. So I cannot choose that. If I want to apply that particular input, I also have to apply the complex conjugate input. Okay? I cannot choose U to be, mathematically, I can set U equal to E to the power JT. In practice, I cannot do it. I cannot have an experiment that does that, right? If I want to do an experiment, I always have to add to a complex conjugate input. So to a complex input, I have to add the complex conjugate so that the input will be real.
Why can't you have only
I mean, how do you create something that is that has a complex number in reality? You cannot. I don't know. I mean, anybody can help clarifying this point?
Can you repeat the question?
The question is, why can't I there's no chalk here. Thank you. Can I apply an input that is E to the power JT? Mathematically, I can, right? I can write a formula that is like that. In practice, can I do that? No. Right? What is this number? This is cosine of t plus j sine of t, right? Okay, this part is fun enough. I can generate a signal that is cosine of time, right? Can I generate this one here? No way. What does it mean? This is not something that is physical. Okay? I can write equations that look like that, but this is not something that I can ever see on a physical experiment. Now, if I really wanted to do a physical experiment with this kind of input, what is it that I need to do? Okay, so this stuff I cannot do, okay? So, but this I can do. Okay, what is this? This would be cosine of t plus j sine of t plus cosine of t minus j sine of t. Can I physically realize this? Yes, because this guy goes away, cancels with this guy here, and what I'm left is 2 cosine of t. Okay? You get the point? So choosing these exponential inputs is a mathematical construct that is great because it allows me to write a whole bunch of very useful formulas. But if S is a complex conjugate, if S is a real complex number, so if S is a complex number which actually has an imaginary part, then I cannot generate that input physically, okay? I can write formulas with that input, but I cannot generate it physically. If I want to do an experiment with that particular input, I have to add the complex conjugate part, okay? Okay, so then everything becomes real again and everybody's happy, okay? Okay, good. Now, okay, so let's go back to the formula, okay? Actually, another example. What if I wanted to apply a constant input? What people call like a unit step. I want u of t to be equal to 1 for all positive time, yeah?
Maybe if sigma is equal to a negative number, so if the convergence to some...
So if sigma is equal to a negative number, if S is a negative number, meaning that it's real, what you will have is a decaying exponential, right? Which is great. Now what I want to have is a constant, but I want to have a constant that is not 0, right? So if you wanted to apply an input that is a constant, not 0, what would you choose for S? 0, right? If I choose sigma to be, if I choose S to be equal to 0, then u, right, so it would be e to the power 0, t, would just be 1. Okay? So you see that this exponential family of inputs allows you to represent constant inputs, allows you to represent anything that is a periodic function, right? Because you can always write a periodic function as some sum of sines and cosines, yeah? Oh, you just multiply it, right? So remember that for linear systems, if you multiply the input by, say, a constant c, what happens to the output is also multiplied by the constant c, okay? So that's why, typically in controlled systems, we talk about unit step, because it doesn't matter. If you want the step to be 23.5, just multiply whatever by 23.5, okay? Scale doesn't matter, okay? Clear? Any other questions? Okay, so now we have to do a little bit of math. Okay, so recall, this is the formula where we started, right? So this is the formula that we already derived. Now, what we are saying is we want to see what happens if I choose my input to be one of these exponentials, right? So we choose that u of t is equal to e to the power st. We plug it in, right? We substitute u of t or u of tau by e to the power s tau and e to the power st, okay? Then what is it that we can do here? Okay, so just look at this, you know, oh my goodness. Okay, now I can stop I don't need the internet anymore. Okay. Really, you should concentrate on this part here, okay? So this is the tricky part. You notice that this exponential just gets to this exponential goes here, right? So we are doing all the math only on this part, okay? So now what I can say is that I can, pull out, all of these terms here are multiplied by e to the power a, e to the power at. I can just pull that out of e to the power at. Notice that the integral, the variable that changes over the integral is tau, right? So from the point of view of this integral, e to the power at is a constant, right? So I can just pull it out of the integral. What I'm left within the integral is this stuff here. In principle, I can also push the b out on the right side, around the right-hand side, right? That's also a constant. So what I had to do is integrate from 0 to t e to the power si minus a times tau d tau. Okay? Now, how do I compute that integral? It's pretty much essentially the same way that you would compute this integral if a was a scalar, okay? So in particular, if si minus a is invertible, that is, if you can compute si minus a inverse, i.e. you can divide by s minus a if a were a scalar, then you do the math, and then this is the result of that integral, okay? Still looks complicated, okay? So what we will do is now we will try to collect terms, and in particular what you will see is that there are a bunch of terms that depend on e to the power st and a bunch of terms that do not depend on e to the power st, okay? And this is how I write them down. So there are a number of terms, this group here, which does not depend on e to the power st. Now, what can you say about these terms? The stuff between the square brackets is, however complicated, is a constant. It's some number or some matrix, okay? And the whole thing gets multiplied by e to the power at. Now, if your system is stable, all the eigenvalues of A have a negative real part, all this stuff under square brackets will be multiplied by some exponentials that go to 0, okay? So that's why I call this stuff the transient response, okay? As long as your system is stable, all this part will just disappear, okay? Will go to 0 eventually. On the other hand, you have this other group of terms, right? Again, between square brackets, what you have is a number, or just a matrix of numbers, okay? That multiplies e to the power st, okay? So as long as your system is asymptotically stable, meaning that the transient response will eventually go to 0, what you are left with is just the steady state part, okay? And look at the steady state part. The steady state part is, now I'm applying an input u of t is equal to e to the power st. The steady state part of the response is again e to the power st, that is exactly the same as the input, multiplied by some number, or multiplied by some matrix, okay? Some constant matrix. I will call that constant matrix G of S. Now, if I think of this as, G of S for any particular choice of S would be a complex number, okay, in general. If I think of G of S as a function of S, then I call this function g of s defined as c times si minus a inverse b plus d. I call that the transfer function. Okay? What is this transfer function? Essentially, that's the complex number that for any value of s, where s is a complex number, gives me how the input is translated into an output in steady state. Okay? Now, the important thing here is that the shape of the output is exactly the same as the shape of the input, multiplied by a matrix that could be complex. What does it mean when you multiply something by a complex number? You remember? When you multiply something by a complex number, think of the complex number. So which form, how do you want to represent the complex number? You want to use the Cartesian representation or you want to use the polar representation? You're multiplying polar, okay? So when you're multiplying something by a complex number, that is the same as multiplying the amplitude of your input by the magnitude of the complex number, okay? And then you are adding to the phase of your input the phase of the complex number, okay? So essentially what you see here, this quantity here is exactly the same as your input, just scaled, amplified, or made smaller, and then shifted in phase by something that would be the imaginary part of your transfer function, okay? For example, if I choose my input to be a sinusoidal signal, I choose S to be j omega, I had to remember to apply also e to the power minus j omega t. That's this sinusoidal function. The output will be given by, so u of t will be given by g of j omega times e j omega t. I had to remember that I also had to add the response to the complex conjugate. So this would be plus g of minus j omega times e to the power minus j omega t, okay? So what will happen is that the magnitude of this guy will be equal to the magnitude of this guy, which is m. The phase of this will be the opposite of the phase of this. So I have something that has phase, say, phi, something that has phase of minus phi, right? You do the calculation here, what you see is that now this is 2m, right? So that is the magnitude times the cosine of omega t plus some phase phi, okay? So now what you see is that we put 2 cosine of omega t as an input. At the output, what we get is another sine wave whose magnitude is scaled by m, where m is the magnitude of the transfer function at j omega, and whose phase is changed by phi, where phi is the argument of the transfer function at j omega. Okay? Again, input is a sinusoid, output will be a sinusoid of different amplitude and different phase in general. Okay? I should have a picture. Let me show you the figure here. Okay, essentially this is what it will eventually look like, okay? So the blue curve is my input, okay, for whatever system, okay, for some system. You see that the output will be, let's say that I have initial condition 0, the output may be this red curve, something like that. And as you can see, this red curve converges very quickly to just a sinusoid of constant amplitude, which is given by this green curve, okay? The difference is in the transient, but you see that the transient dies out very quickly, okay? And as you see, eventually the steady state response will be a sinusoid that is scaled down, right? And whose magnitude is, and whose phase is about 90 degrees. You have like a 90-degree phase delay with respect to the input. Okay? This is just one example in a particular choice of input and system. Okay? So let's get back to this. Now, remember that in general, if we know the response to an input of the form, say, e to the power st, we can find the solution to more complex inputs. In particular, if we know that we have some input u1, and we compute the output to that input is y1, we have another input u2, we compute the output, which is y2, then if I take the first input multiplied by alpha, and I add the second input multiplied by beta, the output will be alpha times y1 plus beta times y2, okay? Superposition. Particular, let's say that we have two inputs. One is, oh, this should have been a 1, clearly, okay? So I have two inputs, u1 power e s1t, and u2, which is u2, where u2 is whatever constant, times e to the power s2t. y1 will be given by this expression, y2 will be given by this expression. Notice that S1 and S2 are in general different, right? Okay? So then if we choose the input to be this one, then the output will be this one, okay? So have the transfer function evaluated at S1 multiply the first input plus the transfer function evaluated at S2 times the second input. More in general, if I have n elementary inputs and I write the input signal as the sum with index I of ui e to the power sit, then I can always compute my steady state output as the sum of essentially the same sum, but where I multiply each term by g of si, okay? Remember that I can do that only if my system is asymptotically stable, right? Because if and only if the system is asymptotically stable, the transient will disappear. Okay? Okay, let's take a break here and then we'll continue after the break. Okay. Okay, let's resume the lecture. I don't know where I can do this, but an example that came up during the discussion with some of your colleagues during a break. Just to give you an intuitive feeling for what this means to this transfer function, right? So just think of, remember when we were talking about the cabin in the woods, right? That you have, right? And, and you're looking at the temperature in that cabin, okay? So what drives the temperature in the cabin, right? So is really the heat from the sun, okay? You can think of the heat from the sun as your input. How does the heat from the sun change during the day? Imagine there are no clouds, no nothing, okay? So it's a clear day, a beautiful clear day, okay? So what you will have is, the sun is, well, on the other side of the world at midnight, right? Let's say that we are around the equinox, right? So then the sun will rise around 6 o'clock, right? We'll reach the maximum, so this is 6, we reach a maximum height in the sky at noon, okay? We'll set at 6 o'clock, 6 p.m., okay? And then, we repeat the cycle, right? So then what is the input? The input clearly is a sinusoid, right? What is the period of this sinusoid?
24
24 hours, right? Now, how do you think that the temperature in your cabin will change? What is the hottest time of the day? Is it noon? 6 p.m., the hottest time of the day? Usually the hottest time of the day is probably around 2 p.m., right? So you see that, and how will the temperature in your cabin change? Will also be another sinusoid. What will be the period of this sinusoid? Is again 24-hour period, right? What is the phase of this sinusoid? Will it be the same as your input? No, it will be a little bit delayed, right? So now your peak will no longer be at 12, right? But will be, say, 2 p.m., somewhere around here, okay? Sorry. Okay, trying to draw. And what you see is that now the input is the solar, say, illumination, right? The output is your actual temperature in the cabin. The input is a sinusoid with period 24 hours, right? And magnitude, whatever, okay? And your temperature will be another sinusoid with some magnitude, which in general will be different, right? Even the units are different, right? The same period and a different phase. By the same token, what is the time of the year when the length of day and night are the same? Or, what is the time of the year where actually, I want to say the other way around. What is the time of the year where the days are longest, right? And you get more sun illumination.
21st June.
Right, is the summer solstice, right? So June 21st, or thereabouts. What is the hottest time of the year? Is it June 21st? No.
Always raining.
In general, right? So, if you look at averages, don't look at, as I said before, just imagine clear days, no clouds and things like that, right? So typically the hottest time of the year is around, like second half of July, August, right? And again, this is not the time where the sun is shining the hottest, the brightest. But you have somewhat of a delay. This is actually called like a phase lag, right? That is due to the fact that, so why do you have this delay? Physically. Yeah.
Okay, so the energy that is conserved in the hottest time in the season.
Right, essentially this is the dynamics of the atmosphere, right? So essentially when you shine the sun on something, it takes some time for that something to heat up. Okay? And, okay, so then you have, you illuminate something, right? And then the temperature of that object will increase. How quickly will it increase? It will be an exponential, right? How steep is that exponential? Well, that depends on the eigenvalue, right, of that particular dynamical system. Okay? This eigenvalue will tell you, how much time, how responsive, how fast your response will be, and that will drive how much of a phase delay you will have. Okay? We'll do more and more and more of this, okay? So we spend the whole semester on these things, okay? Good. Questions? Okay, so this is, now what does it mean in practice to have this formula C times Si minus A inverse B plus D, blah, blah, right? Let's look at an example. So we have a simple dynamical system, which is described by these equations. What is A in this system? Well, it's just -1, B is 1, C is 1, D is 0. So I want to compute what is my transfer function. Well, it's C, which is 1, times Si minus A is just -1, So this will be S minus 1 inverse times B, which is 1, plus 0, plus D that is 0. Okay? So you see that this transfer function is actually given by 1 over S plus 1. Okay? Whenever you have a single input, single output LTI system, I should write this. Okay? Whenever you have a single input, single output LTI system, the transfer function will always be the ratio of two polynomials. Okay? What can you say about the eigenvalues of A and the values at which the denominator essentially goes to 0? They're exactly the same, right? You remember that, how do I compute the eigenvalues of A? Right? The eigenvalues of A are the eigenvalues of A are obtained by setting the determinant of Si minus A to be equal to 0, right? How do you call, so the determinant of Si minus A, what would that be in practice? In general, this would be a polynomial, right? Which is called the characteristic polynomial. If I set this polynomial to 0, this is called the characteristic equation, right? The roots, the solution of these characteristic equations are actually the eigenvalues of the matrix A, okay? This is linear algebra. Probably you have already seen this, okay? Now, one of your colleagues was asking me, oh, but usually we write this as the determinant of A minus lambda I, right? Or A minus Si. What's the difference? Does that impact the values, the solutions? No, right? Because I can just as well multiply this equation by -1 and the solution do not change, right? Okay? Now, when I want to compute the inverse of Si minus A, what is the inverse of Si minus A? How do I compute this matrix here? Ask MATLAB, right? If you had to do the calculation, how will you do it? You know that the inverse of a matrix is computed by, what you have is this adjoint matrix, right? Multiplied by or divided by the determinant of Si minus A. Okay? Okay? So you see that at the denominator of this matrix inverse, you will have exactly the characteristic polynomial. Okay? So what this also tells you is that the eigenvalues of this matrix, the eigenvalues of A, are exactly the roots of the denominator in the transfer function. Is that clear? Or conversely, these are the values of S for which your transfer function will actually go to infinity. Questions? Yeah.
What if A, B, C, D, they are multidimensional, if it's about equal?
Yeah. So if the system is single input, single output, Y will be a number, right? It will be a scalar, and U is also a scalar, right? So A will be a big matrix, but C will be a row vector, and B will be a column vector. So when you do this calculation, what you get is just one, again, a scalar. You see the point? No, but it's a valid point, right? But when the system is single input, single output, C will be a row vector, right? A will be a square matrix, right? And B will be a column vector. When you multiply a row vector times, say, a square matrix, what you get is another row vector. When you multiply row vector by column vector, you get a scalar. Okay? Now, there are what are called the multiple input, multiple output systems in which your C vector, your C matrix in general will have several rows, and your B matrix will have several columns. In which case, you get your transfer function will actually be a transfer function matrix, okay? Where each entry of that matrix will have this form, okay? But, valid point. In this class, we will only do single input, single output systems, okay? So don't worry about the matrix case. For us, the transfer function will just be a function, okay, a scalar function, okay? Clear? Okay. Okay, so in this particular case, what you have is that the transfer function is 1 over s plus 1. Let's try to figure out what is the steady state output given an input u of t is equal to cosine of omega t. Why do I choose this? Just because, okay? So this is just one example. Let's figure out what happens if I give a sinusoid as an input, okay? So we can write, as you know, u of t, if cosine omega t, I can write it as the sum of these two complex conjugate exponentials, okay? Right? So then what is the response to the hypothetical first part of this input? Okay? So u, which is the coefficient by which I multiply the input, is 1/2. S1 is plus j omega. So I had to compute g of j omega times 1/2 e j omega t. In our case, the transfer function is 1 over s plus 1. So 1 over s plus 1 is 1 over 1 plus j omega. Okay? Let's do the same for y2. And what we get is e to the power minus j omega t over 2 times 1 minus j omega. This is, again, the transfer function for x is equal to minus j omega. Let's add these two things together, right? So we know that the output to the combined input will be the sum of the two outputs. Do the calculations, you can go through them, and what you will see is that what I will get at the end is cosine of omega t plus omega sine of omega t divided by 1 plus omega squared. Okay? So what you see is that, essentially what we have here is, again, another sinusoid with frequency omega and some phase, which in general will be not the same phase as the cosine, scaled by 1 over 1 plus omega squared. Okay? What does this tell you, for example? What this tells you is that the higher the frequency, what do you think happens? You are in your cabin, and then let's say that you have a big heater or something, and then you turn it on and off, on, off, off, on, off, on, off, 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 on, off. What do you think will happen to the temperature? You see that the temperature will not change that much, okay? Just because the temperature in your cabin will not change so quickly as you are switching the heater on and off, right? And in fact, you see that, right? When I switch when my input is very high frequency, means that omega is large. So what happens to the amplitude of your response will become, closer and closer to 0. Okay? Actually, my favorite example in this is, well, you're too young to have children, probably, but maybe you have some like a niece or some child in your life, right? And you push them on the swing. What is the frequency at which you push them on the swing? You typically push them once per period, right? So your control input is the same as the natural frequency of oscillation of the swing. If you take your child or your niece or nephew and you do this, what happens? Not much. I mean, well, probably they get upset. They're not having too much fun, right? Because essentially this wing doesn't move at that frequency, right? So their response is a sinusoid, right? But it's not a sinusoid where they actually have fun. It's a sinusoid where they feel miserable, okay? You get the sense? And this is actually typical of all physical systems, that as the frequency of the input goes up, the amplitude of the response goes to 0, okay? Because just physical systems do not respond to things that happen too quickly, okay? Anyway, so this is just an example, and this is an example that we discussed before. Okay? Let's look a little bit at some of the algebra involved in computing this transfer function. So if we have a transfer function, which is given by, again, this is the definition of transfer function. How do we actually compute it? Well, if A is diagonal, I think that you can get the sense that I really like the diagonal form, okay? For me, if you think in terms of diagonal realization of your model, everything is easy, okay? So if A is diagonal, and with eigenvalues lambda 1 to lambda n, how do I compute this inverse? Well, this is easy, right? Because if A is diagonal, Si minus A inverse will also be diagonal, right? And what will be the entries on this diagonal matrix? Will be 1 over S minus the lambdas, okay? So this will be the entries on the diagonal, will be the S minus lambda 1, S minus lambda 2, so on and so forth. When you're computing this whole thing, what you get, oops, I forgot a term here. Okay. When you compute, you multiply by C, you pre-multiply by C, you post-multiply by B. At the end of the day, each one of these diagonal terms will be multiplied by one of the entries in C, we multiplied one of the entries in B. Okay? And then you will have all these terms, and then you will have the D term. Okay? This is when you get lucky and your system is diagonal. In general, this is not the case. What you will have to do is compute the inverse of a matrix in a general form. And as we said before, the denominator will actually be the characteristic polynomial, okay, of the function, of the matrix. The numerator will be some other polynomial, okay? Will be 1 degree less than the characteristic polynomial, okay? And then you have the D term, okay? So this is the general, but this is only algebra. You go and invert this matrix by hand, invert it with using MATLAB, what you will get is something that looks like this. Okay? And by the way, if you take this form, even the diagonalized form, and then you put everything to a common denominator, what you will get is exactly the same. Okay? In a sense, this is a factorized form where you see when you're breaking down the characteristic polynomial into S minus lambda 1, S minus lambda 2 times blah, 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 times S minus lambda n. Okay? Okay, now, a nice thing that you can see from this is that given A, B, C, D, how many transfer functions do you get? 1, right? Because transfer function given A, B, C, D is just computed according to this formula. Okay? Nothing to choose. No, you have no options. Let's say that you want to do the opposite. Now, somebody gives you the transfer function of a system. Now, it is no longer the case that given a transfer function, there is only one choice of A, B, C, D matrices that result in that transfer function. Okay? You may remember when we talk about realizations, I think that we can just transform any A, B, C, D model using a similarity transformation. What we get is something that is exactly the same for all intents and purposes. In particular, so given a transfer function, G of S, there are very many state space models, A, B, C, D, which have that transfer function. how do we pick one A, B, C, D model that we like? Well, there are some models that are better than others. In particular, what we want to have is a ABCD matrix that is as small as possible. Okay? So if the degree of the characteristic polynomial is n, what do you think should be the dimension of the matrix A? Should also be n, okay? The characteristic polynomial, the degree of the characteristic polynomial gives me how many eigenvalues I have, right? The eigenvalues also is, a matrix of dimension, a square matrix of dimension n has n eigenvalues, right? So I really like to have my A matrix to be as small as possible. That is, has to have at least the same dimension as the degree of the characteristic polynomial, okay? In particular, what we say is that we want to have a system ABCD that is controllable, observable, okay? Because there is no point in having some extra modes, extra states that actually I cannot control, I cannot observe. This will not appear in the transfer function, okay? And so we want to construct what are called these minimal realizations. How can you do it? Well, let's do what we did before, but in reverse. If the transfer function is written as a partial fraction expansion, something like it's just a sum of all these terms, what do you think the realization will be? I know that this was the result of having a diagonal A, right? I can construct a system with a diagonal A by choosing all these things. These are the eigenvalues, so I put them on the diagonal. These are all, zeros and zeros, okay? How do I choose B and C? Well, what I know is that the terms at the numerator of all these fractions are actually the products, right? So P1 will actually be the product of C1 times B1. I can choose C1 and B1 however I like, as long as they're not zero. In particular, I can choose them to be square root of P1, right? So then, the terms in C and the terms in B will be the same. You can choose all the terms in C to be ones, okay? And that will be fine. But, this is a particular choice, okay? What if your transfer function is not written as this partial fraction expansion? Well, something you could do is transform it into a partial fraction expansion, if you want. If you have something like that, you can always write it as this sum, if you want. It takes a little bit of work, but you can do it. Let's say you don't want to do the work, then you can verify that if I give you, if I construct my A matrix in this way. So what I do is, I put on the bottom row all the coefficients of the denominator, okay? A0 is the coefficient of the zero-order term in the denominator. So I just put this in the matrix here. This is the minus the coefficient of the first-order term in the denominator, so on and so forth, okay? No thinking, just copy the coefficients into this matrix, okay? Then the rest of the matrix is done with all zeros, except for the terms on the upper diagonal, right? On, just one step up from the diagonal of the matrix, and you set them to ones, okay? The B matrix, you set it to all zeros except for a 1 at the bottom. The C matrix is actually containing all the terms, all the coefficients of the numerator, okay? And D is whatever D you have here. You can do the calculations if you really want, and you can verify that given this realization, the transfer function is exactly what we want, okay? Is exactly this one, okay? This is another, so you can say, but should I use the diagonal form? Should I use this form? What is the answer? It's the same. Both work. Both will give you exactly the same transfer function. Okay? Okay? So as we said, the state space realizations are all the same modulo similarity transformations. Okay? In particular, this is what is called the canonical form, And this is what is called the controllable canonical form, okay? No need to know why and all the details now. Just know that if for any reason you're given a transfer function and you want to build the ABCD matrices, they give you the transfer function. This is one way of doing it, okay? Or the diagonalized form is another way of doing it, okay? You pick. Okay, questions? Okay, now what we will do is, I usually try to avoid this much, emphasizing this too much, because you don't actually need to know Laplace transforms to do this course. On the other hand, if you already know Laplace transforms, it may be useful to establish this connection, okay? So the point here is that what we said is that we can use the exponential inputs as a special class of inputs that are, on one hand, easy to handle, because we know that if the input is some constant times e power st, the output will be some other constant times e to the power st, okay? On the other hand, the question is, okay, but is this a useful class of elementary inputs? The answer is yes, because we know that we can write any function, as the linear combination of these exponentials, okay? How do we do that? Well, that is actually using the Laplace transform and the inverse Laplace transform, okay? So if we have a signal u, and we want to write the Laplace transform, we write it this way, so this is script L applied to u, which gives you another function that we call this capital U, okay? How is this defined? Well, this is a transform, right? So what I do is I take my system U, I multiply by e to the power minus st, and then I integrate over all time, okay? So as you can understand, once I integrate over dt, time disappears, t disappears from the right-hand side, and the right-hand side is just a function of s, right? So then we have transformed our function u, which is a function of time, to a function of s. That's what is called a transform, right? The inverse of this is this L inverse of u, and is defined in this way, okay? Don't be scared, okay? So this is just for you to know that these things exist, okay? So you will never, ever in your life actually compute this integral, okay? Okay? What is important in this integral is the following, that with a little bit of a leap of faith, you remember that before we wrote our input as the sum of a bunch of ui's times e to the power si of t. Leap of faith transform the sum, the finite summation of a finite number of terms into an integral, okay? Now, what you see is that now these u of s are all the coefficients by which I multiply something that looks exactly my elementary input, e to the power st, okay? So if I have any function u of t, and I want to figure out what are these coefficients that I need to multiply these elementary inputs by, how do I find those coefficients? Those coefficients are exactly the Laplace transform of my signal u of t, okay? Right? So what we did before is, if I know that my input is given by the finite sum of terms that look like ui times e to the power sit, then I know that the steady state, my output, will be given by the sum of the same terms, each one multiplied by g of si. Okay? Move it to the limit. Now, instead of having a finite sum, we have an integral. Then what I know is that if my input is written as this sum, or this integral, then I know that my output will be given by a steady state, will be given by this other integral. Okay? And now look at what happens here. What we have as an output, instead of having that that complicated. Okay, so this is what we wrote, what we wrote before. Essentially, now what we have is that the transform of the output can be obtained by just multiplying the transform of the input times the transfer function. Okay? This is the equivalent of that integral that we wrote before. So this is the same thing as that integral that we wrote before, is the integral between 0 and t of e to the power a t minus tau b u of tau d tau. Okay? So essentially, this thing here and this thing here are exactly the same thing. Okay? One corresponds to the other. And you see that here what you have is just a multiplication of a transfer function times this transform. Here you have this complicated integral. Okay? So this is why this transfer function is really that useful, because it allows you to compute in a very easy, and believe me, at some point will become understandable way, what is the effect of certain kinds of inputs. Okay? Inputs are exponential, outputs are just the same exponential multiplied by this complex number that is g of s. Okay? Okay, so that we can summarize here, actually a little bit early today, but essentially what we have looked at today is this idea of this response to, so there are some inputs that are actually easier to handle than other inputs. The inputs that are easier to handle are these exponential inputs. Why? Because I know that if my input is an exponential, e to the power st, my output will be some constant, some complex number, g of s, that multiplies e to the power st. Okay? What is this g of s? If you think of it as something that is a function of s, this is what is called the transfer function. Okay? We have seen how to construct the transfer function given the A, B, C, D, the state space model. And we have seen how to construct the state space model given the transfer function. So we can go both directions. Okay? The fact that we can go both directions, what it's telling you is that a transfer function is as good a model as the state space model, is as rich. Okay? But it is much easier to use when you want to do control design by hand, pencil, and paper. Okay? State space model is something that you will use when you're doing control design by MATLAB. Okay? So transfer function what we'll use in the future, and then we establish this connection between transfer functions and Laplace transforms. Okay? You may have noticed that when we multiply things by e to the power st, that's essentially the operator that is used when you compute the Laplace transform. Okay, it's the same thing. Okay, any questions? No? If not, then thank you, and I will see you next week.